We're going to be doing some problems from chapter 10 about gases. And on the other videos, I left off on problem 50. So ready for problem number 52. And I have about 10 problems to do. We'll see if we get through all of them on this video, excuse me. So here, I'm going to do a switch share. And turn this light on. And we're looking at number 52. Under which set of conditions will chlorine deviate least from ideal gas behavior? So what is ideal gas behavior? An ideal gas is one where PV equals nRT. So what does that mean? Well, it means that when you measure the pressure of the gas, you measure the volume of the gas, you know how many moles of gas you have, because maybe you know its mass, and you converted that to moles using molar mass, and you know the temperature of the gas. When you plug all those numbers in, you get like 5 equals 5 or 10 equals 10. If you get 10 equals 9, well, it's not really ideal. It's close to ideal, but not ideal. So what makes a gas not ideal? So a non-ideal gas. And a non-ideal gas is really just a real gas. So what is it about a real gas that makes it non-ideal? Well, you have to think about the kinetic molecular theory of gases. And the two parts of the kinetic molecular theory of gases that aren't really real is that the volume of a gas is equal to the volume of the container. That's not really true. This volume of the gas is supposed to be the volume that the gas particles have to move around in. So if these are your gas particles moving around, and this is the volume of your container, what happens if you take these particles and you condense them? So you don't let them move around. So here's the particles, and this is the real volume of the container that the gas particles have to move around in. You can see that the real volume is smaller than the volume of the container. Okay, so that's one correction. Real gases don't have as much volume to move around in as ideal gases. So remember, this is ideal. Ideally, they have the full volume to move around in. In reality, they don't. Another thing that we have about ideal gases is that in the ideal gases, the particles have elastic collisions. And the reality is they don't have elastic collisions, so that when they hit, and this length of this arrow is the energy with which it hits, when it bounces off, the energy becomes a little less. That's really what happens. Some of the energy is lost. Now you might think, well, then gases should eventually turn into liquids. And the idea here is that actually the wall of the container gives some energy back to the particles. So that's how the gases don't ever really lose any energy. They behave like they're elastic, but in fact, they're not. Okay, so we have non-elastic collisions. Now, there have to be corrections for this. So when we look at PV equals nRT, and this is ideal, we have to have a correction for the volume. So the volume is V minus Bn. So what is B and N? N is the moles of gas, and B is a factor that depends on the gas molecule. And B basically describes the volume of the gas molecule. The larger the volume of the gas molecule, the larger the B, because if you have a larger B times N, you're taking away more volume from the real volume. So this is the real volume available. And that's the way I like to think about it. Okay, so what about the P? Well, here, when you measure the pressure here, it's actually less than what the real pressure is, because here, the pressure we're measuring is after it kind of bounces off. So we've got an addition factor here. So this is P, and I want to say that it is A squared over N or something like that. Shoot, let's just look it up. Okay, so where do we go from here? So it's plus A times N over V squared. Now, A depends on the gas. Depends on gas. And A depends on the gas. N is the moles of the gas particles, and V is the volume. So this is kind of the extra pressure we add to the molecules. And here, A is basically the stickiness factor of a gas. If we take a look at some values for A and for B, you can see what they look like here in the book. For instance, if you look at H2O, which is a polar molecule, and therefore it sticks to other polar molecules very well, it's got a very high A value. If you look at chlorine, which is a large molecule, it also has a high A value because when you have a lot of surface area, you stick to other things better also. Helium, you see, is a very small atom, so it has a small A. So generally, the size of the particle has a lot to do with its A value. All right, now it's a little bit more than that, but we'll just leave it at that. The B value depends also on the volume of the particle. Okay, helium, small particle. H2O is a little bit bigger than helium, atom-wise and so forth. And you can see that Cl2 is quite a bit bigger than either of these, and it has a very large A value. Now, which of these should you memorize? And the answer is none of them. None of them. Okay. So this equation here is called the van der Waals equation. At least that's the way what we used to call it. And it is for real gases. Now, it's important to understand that we're going to be adding a factor that increases the overall pressure from the ideal. So, and here, this is going to be the, and I should say this is the ideal pressure, and this is the ideal volume. And here, we're going to make a correction to the ideal volume. We're going to make it smaller. So if we're multiplying these two values together, and we make one larger and we make one smaller, the end product is it's pretty much going to be the same product. So for instance, if it was 10 times 10, that'd be 100. But if we say, well, you know what, that should really be 11, and this one should really be 9, now you have 11 times 9, which is 99. So how does 99 compare to 100? Well, they're pretty much the same number. Okay. Now, the other thing you want to know is, when are ideal gases really not ideal? And the answer is really simple. When you have a really low temp, and the reason for a low temp that they're not ideal is because kinetic energy is proportional to the temp in Kelvin. And if you have a low temp, you have a low kinetic energy, which means that stickiness factor is going to play a bigger role and you will stick together better. So the molecules stick together better. And that means if they stick together better, they're going to become a liquid. So when you lower the temperature of a gas, you lower the kinetic energy of the particles, they end up sticking together and you turn it into a liquid. And we know that, right? Because if you raise the temperature of a liquid, you turn it into a gas because you're adding energy. Well, if you lower the temperature, you're taking away energy. How else can we get those molecules to stick together? Well, you increase the pressure. So high pressure is another way to make an ideal gas not really ideal. So when you increase the pressure, what you're doing here is you're essentially removing space between the gas particles. And if you remove enough space between the gas particles, so here's increasing pressure. We have 5 particles, and now we're going to change the volume so that the pressure has to go up. And here's my 5 particles, and you can see they're starting to touch. So by increasing the pressure, we have now turned this into a liquid. Okay, so these are the 2 factors where an ideal gas is not really going to be that ideal: low temp and high pressure. Okay, so now that we know that, under which set of conditions will chlorine deviate least from ideal gas behavior? So deviate least from ideal gas behavior. To me, that means be most ideal, right? Because to deviate from ideal gas means not ideal. So we need to think about, well, what seems to be regular, if you will, pressures and regular temps? Well, I would say that 1 atmosphere is definitely a regular pressure. Absolutely. And 0 degrees Celsius, well, that seems to be a pretty regular temp. So I think A does not deviate very much. Now for B, we've got a really low pressure, but low pressure doesn't do anything to the gas. We're looking for high pressure and high temp. So this is a high temp and this is a low pressure. So, you know, with maybe this one is deviating a little bit. Now here we have a pretty high pressure, 10 atmospheres. And this temperature is kind of low, just like this one is kind of low, but not too bad. You know, if you really want to think about where do we want to be for the right temp for an ideal gas, and the answer is probably around 20 degrees Celsius. But we have something called STP, standard temp and pressure. Now, standard temp pressure is based a lot on when a gas is going to be ideal, standard temp and pressure. Okay, so what is the standard temp? The temp is 0 degrees Celsius. So that's ideal. And the pressure is 1 atmosphere. That's the definition of STP. So you can see that A is really STP conditions. B is going to be low pressure, but we aren't bothered by that. But this is kind of high temp. So we are bothered by high temp because remember, high temp, low pressure, or high temp, I should say low temp, high pressure we're kind of bothered by. So this one, you know, I'd say actually not too bad. C, we've got high pressure, which we don't like. Whoop. And we've got STP temp. So we're okay with that. And for D, we've got the STP temp or pressure, excuse me, but we've got kind of a high temp. So overall, we're going to say, well, you know what? That's where it's going to deviate the least because it's standard temp and pressure. All right, so that's number 52. Keeping this all organized. All right, let's look at number 58. So we skipped a few of these. On combustion, one liter of a gaseous compound of hydrogen, carbon, and nitrogen gives 2 liters of CO2, 3.5 liters of H2O vapor, so that's a gas, and 0.50 liters of N2 at STP. What is the empirical formula of the compound? All right, so they're saying that combustion of this compound gives us all of these things. All right, so we know there's carbon. I'm going to put X for carbon. We know there's hydrogen. I'm going to put Y for hydrogen. And we know there's nitrogen. And I'm going to put a Z for nitrogen. So compound of hydrogen, carbon, and nitrogen. and I just put these in alphabetical order. We're going to react it with oxygen, and we're going to get CO2 gas plus H2O gas plus N2 gas. Now, all of these gases, for them, we get respectively 2.0 liters of CO2, 3.5 liters of H2O, and we got 0.50 liters of N2. And for each of these gases, the pressure is 1 atmosphere. And that's 1 atmosphere exactly. So I'm not sure why I'm writing 1.00. That's 1 exactly because that's the definition of STP. And the temperature is 273.15 K. Now the definition of STP is 0 degrees Celsius exactly. When we add 273.15, that's not an exact addition. So it's only good to the 100th there. Okay, so this is what we get for the gas. And so this means that we basically have a container, a bag, if you will, of gas, where the pressure is 1 atmosphere. The temperature is 273.15 K. And we have 2.0 liters of CO2, 3.5 liters of H2O, and 0.50 liters of N2. And remember from Dalton's law of partial pressures, the partial pressure of CO2 plus the partial pressure of H2O plus the partial pressure of N2 has to equal 1.00 atmospheres. The sum of the pressure of each gas, which is the partial pressure of that gas, is the total pressure. Okay, so what is the empirical formula of the compound? I think it's safe to say that we need the moles of carbon, the moles of hydrogen, and the moles of nitrogen. Okay, so here's a perfect way to do this. To get the moles of carbon, we can use PV equals nRT. So the moles of carbon is going to be PV over RT. We have the pressure. Well, actually, I don't. Let's see. Oh, I don't think this is written the way. I don't think this is written the way I think it's written. I think that actually this is not the case, but this is the case. You got 2.0 liters of CO2 with 1 ATM. You got 3.5 liters of H2O at 1 ATM. And you got 0.5 liters of N2 at 1 ATM. I'm pretty sure that's what they mean by each of these gases. They're not all in the same container, they're separate. I'm pretty sure that's what they meant. Okay, so otherwise, this is just a real nightmare to do. You don't really have enough information to do this. So to get the moles of carbon, what we're going to do here is we want to get the pressure, the volume, the R, and the T, if you will, right? But here's the deal. We're actually going to get the moles of CO2, and we'll get the moles of CO2. And the deal is with CO2 is 1 mole of CO2 is equal to 1 mole of carbon. So where do I get that from? From the actual formula. 1 mole of CO2 is also equal to 2 moles of oxygen. Okay, so with that in mind, let's calculate the moles of carbon. So for carbon, we've got the moles of CO2 is equal to PV over RT. The pressure is 1 atmosphere exactly, STP. The volume, they say, is 2.0 liters. R, we're going to use the 1 that has atmospheres in it, so 0.08206 liters atmospheres mole K. And for the temperature, we're going to use 273.15 K. Okay, so when I use my calculator here to figure out what the answer is, kind of my go-to for 0.0826 times 300-ish, my go-to is about 25. So 2 over 25 is the same as what? 1 over 12. So 112 puts that at like 0.01 or, excuse me, 112 puts that at about 0.1 or maybe 0.08 or something like that. So let's see what we get. 2 divided by 0.08206 and also divided by 273.15. Now this is equal to 0.08922 moles of CO2. Now we're going to take our 0.08922 moles of CO2 times 1 mole of carbon per 1 mole of CO2, which is also 0.08922 moles of carbon. For nitrogen, we're going to do the same thing. We're going to take the moles of nitrogen are going to be the pressure, 1 atmosphere, times the volume, 0.50 liters, over 0.08206 liters atmosphere, mole K, and the temperature, 273.15 K. Okay, so this answer should be about 1/4 of this answer because the only thing that's changed is the 0.5 versus the 2. So I've got 0.5 divided by 0.08206 and also divided by 273.15. And I get 0.02231 mole of N2, but I really want moles of nitrogen. So to get the moles of nitrogen, I'm going to say 0.02231 moles of N2 times 2 mole of atoms of nitrogen per 1 mole of N2. So here I get 0.04614 moles of nitrogen. And now we do the same thing for hydrogen. So here we have 3.5 liters of H2O. So the moles of H2O are going to be 3.5 liters. Well, I should put this the same as I've done these other calculations. I should start off with 1 atmosphere times 3.5 liters of H2O over 0.08206 liters atmospheres, mole K, and times 273.15 K. Now this answer should be 7 times greater than that answer. And I get 0.1561 mole of H2O. And this should be hydrogen here, not oxygen. So to get the moles of hydrogen, I'm going to start off with my 0.1561 moles of H2O and multiply by 2 moles of hydrogen per 1 mole of H2O. And I get 0.3123 mole of hydrogen. So now that I have the moles of carbon, now that I have the moles of nitrogen, and now that I have the moles of hydrogen, I can simply do this. This is the way I like to do it. 0.08922, hydrogen 0.3123, and nitrogen 0.04614. And I divide each of these by the same amount, the smallest number available. So I'm going to divide each of these by 0.04614. Now, nitrogen will end up being 1. That's pretty clear because you're dividing the same number by the same number. Let's see what happens when we divide 0.08922 by 0.4614. Oops. By 0.04614. And I get carbon 1.93. In hydrogen, we get 0.3123 divided by 0.04614, and I get carbon or hydrogen 6.76. So, I'm not sure if I like these numbers well enough to assume that they're going to round off to whole numbers, but I'm going to do it anyways. So C2H7N, and I think that might be the empirical formula of the compound. So that's the way I would tackle this problem. Okay. All right. So we'll put that one off to the side. Still keeping track of everything. If 12 grams of oxygen is required to inflate a balloon to a certain size at 27 degrees Celsius, what mass of O2 is required to inflate it to the same size and pressure at 5 degrees Celsius? So here's the problem with this one is that we know that to inflate it to the same size at a lower temperature, you're going to need more oxygen because at a lower temperature, you have less pressure and so forth and so on. So you might say, well, you know what? If it's at 5 degrees Celsius, I'm going to need, well, looks like there's 5 times difference. I'm going to need 5 times as much oxygen. What's the problem with that thinking where this is 27, this is 5, and there's about a 5 times difference? And the answer is we never do gas problems in degrees Celsius. We do them in Kelvin, right? So when we look at these two situations, we've got 12.0 grams of O2. It's a certain size, so we're going to call that V. And it's not 27 degrees Celsius. It's 300.15 K because 27 plus 273.15 is 300.15 K. So that's one balloon. The other balloon, same size and pressure, so the volume is V. And here we're going to say the pressure is P, the same volume and pressure. And we want to know how many grams of O2 are needed to do this. And here at 5 degrees Celsius, we're talking about 273.15 plus 5. So that's 278.15 K. It's kind of interesting here. They use 27 point and here they use 5.0. I guess that both of these temperatures are both measured with 2 zig figs, but here it doesn't make any sense. I mean, if you have a thermometer that measures to a tenth, it should be able to measure to a tenth at 27 degrees Celsius also. So here are our two containers. Now, we know that PV equals nRT, and here PV equals nRT. And more specifically, I'm going to put the moles for 12 grams of O2, RT. And actually, I'm going to do this. I'm going to change this to PV over RT is equal to N. And here, I'm going to put PV, and I'm going to do one more thing. I'm going to put PV over R is equal to NT. And here, I'm going to put PV over R is equal to NT. So these are for these two different containers. So this is for my 12 grams of oxygen, and this is for my 300.15 K. This is for my X grams of oxygen and my 278.15. So you might be wondering, well, why is he doing this? Well, what is the pressure of this container versus the pressure of this container? They're the same. So those are the same P's, pressures. The volumes are the same size. So that V is that V. They're the same. These two V's are the same. And R we know is the same. So whatever value this is that I have the box around, that's the same value here. So therefore, we can say that the moles of 12 grams times the temperature is equal to the moles of X grams times the temperature. So that means that here, if we're supposed to figure out the grams to inflate this, we've got a good start. So we can say here that how do you calculate the moles for 12 grams of oxygen? Well, we would say 12 grams of O2 times 1 mole per 16 grams of O2 would give us, let's see, 0.75 mole of O2, if I'm not mistaken, because this is the same as 3 over 4, which is 3/4. Okay, so we know how many moles we have here. So here we can say that NX is equal to moles of that 12 grams of oxygen times the temperature of that 12 grams of oxygen, and that's the one where it's 300.15, divided by the temperature of this oxygen, which is 278.15. So when we plug the numbers in here, we get 0.75 moles times 300.15 K over 278.15 K. Okay, so I'm going to cross the K's out, and we get the moles of oxygen are going to be, let's see, 0.75 times 300.15 and divided by 278.15. So we're going to get 0.809 moles. So we actually need more moles of oxygen here to get the same pressure. And the reason for that, of course, is because we have a lower temp. So lower temp, less kinetic energy, which means you need more molecules to reach the same pressure. So we're almost home free. To get the grams of oxygen here, we're going to take the 0.809 moles of O2 multiplied by 1 mole per 32.00 grams. Oops, I did that upside down. And I know that because I would get the wrong units. Ooh, and that reminds me, I made a mistake there, didn't I? That's 32 grams of O2. And so that means this is not 0.075, it's 0.75 divided by 2. Maybe you caught this before I said anything. So that makes this 0.375. And that makes this 0.40, let's see. .405. And let's see, and that makes this 0.405 times 32 grams per mole, which means that we need 12.9 grams of oxygen. So we need a little bit more oxygen than we had to begin with because the temperature has decreased. Now, an interesting thing here, though, is that when you take a look at the moles of X is equal to T at 12 grams. Well, it's equal to N, T at 278.15 times NX, or actually, I'm screwing this up. let me get a new piece of paper here. We can see here that the N of X is equal to N of 12 grams times the temperature of the 12 grams divided by the temperature of the X grams. Okay, and we know what these temperatures are, so we can plug them in. But this NX and N of 12 grams is going to be proportional to the actual grams, right? Because here, if you have 12 grams, you're going to get a certain N. And if you have X grams, you're going to get a certain N. And the way that these are proportional, these will be proportionally the same way. So we could have just written here that the grams of X will be the same proportion as 12 grams times the 300.15 K over the 278.15 K. And we're probably going to get 12.9 here also. I should remind you here that this 12.9 grams would be rounded to 13 grams, 2 zig figs because of the 12 way up here. Well, actually, we got to use 12.0, so it would be 12.9. Okay, so that's 12.0. Let's see what we get using this ratio. So 12.0 times 300.15 and divided by 273.15, and we get pretty much the same answer, a little bit different. It's 13.2 grams. So probably some rounding error that I did down here made the difference. All right, so that's that problem. A bicycle tire has an internal volume of 1.52 liters and contains 0.406 moles of air. So this is a mixture, but that's all right. We don't need to worry about that right now. The tire will burst if its internal pressure reaches 7.25 atmospheres. What temperature in degrees Celsius does the air in the tire need to be heated to cause a blowout? Okay. So we've got a tire. Here's the rim. And inside here, we have 1.52 liters. We have 0.406 moles of air. And here, the internal pressure, well, we don't have that right here. The tire will burst if its internal pressure reaches 7.25. So that means here it'll burst. So this is my tire bursting. That's the hole being made. If the internal pressure reaches 7.25 atmospheres. So what temperature in degrees Celsius does the air in the tire need to be to cause the blowout? Well, we still have 1.52 liters of gas in here. The idea here is that the volume of the tire doesn't change when you pump it up. And you know that's pretty much the case with car tires or with bicycle tires. Once you get a certain pressure in there, the volume stays the same and the tire doesn't get any bigger, but then all of a sudden it just blows. So here we still have the 1.52 liters, and here we have 0.406 moles of gas. So we need to figure out what temperature in degrees Celsius does the air in the tire need to be? Well, we use PV equals nRT. So this looks like we're doing some sort of a change here, but we're not really. All we're doing here is saying, okay, we're heating it up, okay? We don't have the initial temp, so it's not really a change. We just don't want to know at a particular temp, when will it burst? So this is what we have. So we're going to have the T is equal to PV over NR. Now remember, they want the degrees Celsius, so the answer we're going to get is in Kelvin. So the pressure is 7.25 atmospheres when it bursts. The volume is still 1.52 liters right when it bursts. Of course, after it bursts afterwards, it's going to be a bigger volume because it spreads out. The moles of gas is 0.406. And what are we going to use for R? We're going to use the R with atmospheres in it. So 0.08206 liters atmospheres mole K. So here we can see that the atmospheres cancel, the liters cancel, the moles cancel, and the K doesn't. So we're going to get K for our final answer. And when we estimate this, I guess the way I'm going to figure this is 0.4 goes into 1.5 about, well, 4 times. 4 times 7 is about 28. We'll call it 30. And 30 divided by 1/10 is 300. So this should be around 300 K if I did my estimate correctly. Okay, and I actually get 331 K. So what is the temperature in degrees Celsius? Well, the temperature in degrees Celsius is going to be 331 K minus 273.15. Remember, to turn it into K, you add 273.15. To turn it back into degrees Celsius, we've got to subtract. So minus 273.15. And we have the temperature would be 57.6 degrees Celsius. And that's a pretty hot day. What is this temperature in Fahrenheit? Do you guys remember the formula for Fahrenheit? Isn't it that degrees Fahrenheit is 9/5 degrees Celsius plus 32? So let's figure out what this is in Fahrenheit. We've got 9/5 times 57.6 plus 32. So times 9 divided by 5, and then add 32. And that happens to be 136 degrees Fahrenheit. So that seems like a pretty hot day. I don't know that I've ever seen a day that's hot. Okay, so I'm going to put that down. Now that I see this, it says a bicycle tire. Bicycle tires do have rims, but they're not quite the way I drew it. Let's see how many more problems we have. 1, 2, 3, 4, 5, 6. So we'll do one more and then we'll call it quits. And we'll finish the rest another time. So if you place 2.25 grams of solid silicon in a 6.56 liter flask that contains CH3Cl with a pressure of 585 millimeters of mercury at 25 degrees Celsius, what mass of dimethyl dichlorosilane can be formed? This sounds like one of those limiting reactant types of problems, right? Because here we have this, and here we have this, and we want to know how much of this can form. Well, maybe we have extra silicon. Maybe we have extra, this is called chloromethane. So how do we do this? Well, we need the molar masses of each of these things. So I'm going to write silicon, the molar mass is 28.09. 2CH3Cl, the molar mass of this stuff, is going to be 12.01 plus 3.03 plus 35.45. So the molar mass of this is 50.49. Now, what is the molar mass of silane? Well, a carbon is 12.01, 3 hydrogens is 3.03, and then since we have 2 of those, I'm going to multiply by 2. Then I'm going to add the 28.09 for the silicon. And then I'm going to add 35.45 for the chlorine, but times 2, that's 70.90. And we get 129.07. So those are the molar masses for each of these. So the way I like to do this is if we want to find out how much of this we're going to make, we're going to start with our 2.25 grams of silicon, multiply by 1 mole of silicon per 28.09 grams of silicon. And then we're going to multiply by 1 mole of, we're just going to call this silane for short, per 100 and, oh, excuse me, per 1 mole of silicon. And then we're going to multiply by 129.0 grams of silane per 1 mole of silane. When we multiply these numbers out, 28 should go into that about 5 times. 5 times 2.25 is around, well, I don't know, 12, something like that. And we get 10.34 grams of silane. And that's good to the 3. Now, for the chloromethane, they give us the pressure, the temperature, and they give us the volume. So what we're going to do here for that is we're going to actually calculate first the moles of silane or dichloromethane, and then convert that into grams and so forth. Well, and then convert that into moles of silane and then convert that into grams. So we're going to do this kind of in 2 parts. We're going to do this, and we're going to get the moles of CH3Cl. We're going to use that to get the moles of silane, and then we're going to use the molar mass of silane to get the grams of silane. And we're going to compare these 2 numbers. Whichever number is the least, that's how much we're actually going to make. Okay, so here to calculate the moles, we say N is equal to PV over RT. The pressure is 585 millimeters of mercury. The volume is 6.56 liters. For the R, we're going to use the 62.37 millimeters of mercury per mole K because we want the pressures to cancel. And this is the R that has millimeters of mercury in it. And the temperature is going to be 25 plus the 273, which is 298.15 K. Okay, so that'll give us the moles of, if you will, CHCl3. So let's see what we get here. So roughly that'll go into that 2 times. 2 times 6.56 is 13. 13 will go into 62, something like 5 times. So we get 1/5 or 0.2. and we get 0.206 moles of CH3Cl. So now we're going to take that and convert that into moles of silane and then grams of silane. So here we have 0.206 moles of CH3Cl times 1 mole of silane per 2 moles of CH3Cl, and then times 129.07 grams of silane per 1 mole of silane. So my estimate on this is going to be 2 will go into that and make that 0.1. 0.1 is 1/10. 1/10 of 129 is 12.9. So I should get about 12.9 here. So I get 13.3 grams of silane. So what mass of dimethyl dichlorosilane can be formed? The answer is 10.3 grams of silane can be formed because it's the lesser of these two. That's the first answer. And what pressure would you expect in this same flask at 92 degrees Celsius on completion of the reaction? So to get the pressure of the gas, we know that we have 95 degrees Celsius. We know that it is a 6.56 liter flask, and we're assuming the flask can't get bigger or smaller. And we know that we have 10.3 grams of silane. And again, we're trying to get the pressure. So we're going to use PV equals nRT, which means that the pressure is going to be nRT over the volume. Now to get the moles, we're going to say 10.3 grams of silane times 1 mole of silane per 129.07 grams of silane. And that'll give us how many moles of silane we have. Okay, and I get 0.08011 moles of silane. So we're going to use that here, 0.08011 mole. And here, this should be rounded to that first one, but I'm carrying an extra digit along. For the R, we're going to go ahead and see what kind of answer they want. What pressure, they didn't say if they want the pressure in atmospheres or millimeters of mercury. I'm going to get it in millimeters of mercury because that's what they gave us initially. And I'd like to know what the answer is compared to the initial pressure in the flask. So for the R, I'm going to use the 62.37 liters, millimeters of mercury per mole per K. The temperature is going to be 95 plus 273.15, which is going to be what, 368.15 K. And the volume is still 6.56 liters. So I'm going to estimate this one real quick. 6.56 goes into 62 10 times. 10 times this is 0.8. And 0.8 is almost 1. So 0.8 times 368 is going to be almost 368, but less by about 20%, to be honest with you. So we're going to say that this answer here is going to be about 300. 300 what? Millimeters of mercury. So times 62.37 times 368.15 and divided by 6.56. And I get 280 point, because we want 3 zig figs, and that's millimeters of mercury. Okay, so you can see that the pressure went down from what we originally had, even though the temperature was higher. So why did the pressure go down? And the answer is really simple. For every 2 molecules of CH3Cl, we only ended up with 1 molecule of gas here. When you have half as many gas molecules, you're going to half the pressure. So the original pressure was 585. Half of that would be around 300. Okay, so that's why the pressure decreased. Alrighty then. So that was number 64. That over here. Thank you for listening. My next video will start up with number 72 and we'll go through about 5 problems. You have a good one.